Alright, next planet we're talking about is Jupiter. Jupiter is the largest planet. It has a semi-major axis of 5 AUs. So it's 5 times further away from the Sun, which means that its period, its revolution period around the Sun, is about 11.9 years, close to 12 years. So it takes quite a while to go around the Sun. Its mass is 318 times the mass of the Earth. So this is the first planet we've got to bigger than the Earth, 300 times more massive, and its diameter is 142,800 kilometers. Like, what's that mean? Well, remember that the Earth was at 12,000, so this is about 12 times bigger. So you could fit 12 Earths across Jupiter's diameter. Now Jupiter is what we call oblate, because it rotates rapidly. Its rotation period is around 10 hours. You're like, why am I saying around instead of exactly how fast it is? Well, it shows differential rotation. Remember what differential rotation is? We talked about that with the Sun. Is that where you are on the planet, you're going to rotate at different speeds. It rotates fastest at the equator, slower as you go towards the poles. Oblate means it's flattened. Flattened is because it's rotating so fast, essentially the equator is bulging out. If this is the North Pole, this is the South Pole. Oblate means it's a flattened curve like that. Prolate would be an extended one like that. And so the reason for that is because even though it's much bigger than the Earth, it's rotating much faster. Its period is half as much. So it's rotating so fast, the equator is actually expanding outward. So if you measure the distance across this way, it's longer than if you measure it this way. All right. Let's talk about what we think the interior of Jupiter looks like. Oh, by the way, the density is the other one I want to put up here. Density is 1.3 grams per cubic centimeter. Remember that for the terrestrial planets, we're up around 5 for Venus, Mercury, and Earth, and around 4 for Mars. This is significantly lower. What this means is that Jupiter is mostly gas. Okay? Water is at 1 gram per cubic centimeter. So the outer layers are just gas. In fact, it's mostly gas with some thicker and probably a solid core deep in. So let's talk about that. What we think the interior of Jupiter is like. We think that Jupiter has a small rocky core, maybe about Earth size. A solid core in here that's probably about Earth size, give or take. Okay? And then around that we have a region here which we call our metallic hydrogen layer. And that should be circular, but and then we have the outer layer, which is the molecular hydrogen. Like hydrogen, yeah, because Jupiter is 90% hydrogen. Its composition is very similar to the Sun, where it's mostly hydrogen and helium, and then it has a little bit of all the other stuff in it. But hydrogen is extremely reactive, and so hydrogen reacts with everything. That's why we have the molecular hydrogen. That's where you get water, you get CH4, you get ammonia, methane, ammonia, all kinds of things. Notice they all have hydrogens in them. Hydrogen reacts with everything in there. And then as the pressure gets higher and the temperature gets higher, you get to a region where hydrogen acts like a metal. If you remember on your periodic chart, hydrogen's way over on the left side where all the metals hang out. Okay? And so it can have properties of a metal. It can be conductive, and when you put it at enough pressure and temperature, it enters that region, which we don't have on Earth, but it does in Jupiter. that spinning of this metallic hydrogen core here is what probably makes Jupiter's magnetic field. Jupiter has an extremely large magnetic field. I mean, it's second only to the sun's in size. Very large magnetic field. All right, so that's what we think it would be like, but why do we see it like this? Well, these are what we call cloud bands. Okay? Notice there's a white cloud band here, and a red one here, and a red one that goes white, and it kind of alternates all the way down. Those are called cloud bands. You're like, why do we have cloud bands like that? Well, what you're really seeing when you see these different colors is you're seeing different layers in the atmosphere of Jupiter. Jupiter is almost all atmosphere, but you can see deeper and further out. This is the great red spot, and it's actually more of a hole through the clouds. You're seeing deeper into the clouds. So the different colors are depth. Now remember I was talking about differential rotation. Well, what we find on Jupiter is, here's the North Pole, here's the South Pole here, is that the fastest it moves is at the equator. But then it's slower, and then it's faster, and then it's slower, and it's faster, and it goes this way as it goes out. It goes just the opposite as you go up to the South Pole. So instead of like on the sun where it just goes directly down here, the center of the equator rotates the fastest, but then this region appears to be going backwards, and then this one go forward and backwards. That creates these distinctive cloud bands. And if you were going to try to like navigate, let's say you wanted to use a balloon like a weather balloon on Jupiter, well, if you went in this one, you would get way ahead, but if you wanted to go backwards, you would go into this one, and you could rotate, and by changing your latitude on Jupiter, you can change which direction you're moving on Jupiter. By the way, this is the moon down here. We'll talk about the moons of Jupiter later. But it's a differential rotation, which causes the depth you see into it, which causes the different colored cloud bands. And you see you get these storms. That's what the great red spot is. It's a giant storm. Those come pretty much, here's some smaller ones right here, at the intersection of these cloud bands. You create these different storms. And let's talk about the storms here. So let's see another picture. Here's another picture. These pictures were all taken by satellites. This was, I think, taken by the Cassini mission as it flew to Saturn, but it passed Jupiter on the way. The other one previously was a Galileo picture, which was a probe sent out just to take pictures of Jupiter and study it. Beautiful picture, lots of detail. Better detail than you could ever see from Earth. All right, and this is what I showed here, where you have this rocky core, the metallic hydrogen, the molecular hydrogen layer. Notice that the temperature in here is very hot. It's 25,000 degrees. That's hotter than the temperature of the surface of the sun. Not quite hot enough to create fusion. If Jupiter had been just a little bit bigger, the pressure would have created a high enough temperature, and the hydrogen in the core could have started fusing, and we would have been in a two-star system, a binary system. But it didn't quite happen. Jupiter just didn't quite make it. All right, and then this is as you fall into Jupiter. So this is it. Remember, it's all gas, so there's no real surface. Surface is way, way, way down there somewhere. So as you go in, this is the temperature. It's cold out here in space, but then the temperature starts to increase as you go in. And notice that the different types of clouds have different colors, and so what depth you're seeing, or what cloud you're seeing, is what depth you're seeing into it. Notice the dark red that you see in the great red spot is you're seeing deeper into the cloud layers of Jupiter. Here's the great red spot. So, interesting thing about the great red spot is that it is what we call an anticyclonic storm, meaning it's rotating this way. Or what we would say is rotating counterclockwise, spinning that way. So if it's rotating counterclockwise, or let's think about it on the Earth. If you pay attention to like hurricanes on the Earth, all the ones in the northern hemisphere spin counterclockwise. That's because they're created around a low pressure region, which means there's less air, and air is rushing in, but as it rushes in, because of the spin of the of the Earth, the Coriolis effect makes it spin around this low pressure zone. The lowest pressures ever recorded are at the center of these hurricanes. But in the southern hemisphere, their storms all spin clockwise. But here we have a counterclockwise spinning storm in the southern hemisphere of Jupiter, which means we call this an anticyclonic storm. This is the great red spot, they call it. And as far as we know, it's been around for, well, at least 500 years, since they started seeing it in the 1600s, when they first, well, 400 some years. Once they had telescopes good enough, they've seen it, and it's been there ever since. Okay? Anticyclonic storm means it's around a high pressure. Now, if you think about hurricanes on Earth, what makes a hurricane on Earth stop is it runs into land or it moves north or south. Hurricanes all start where the water is very warm in the summertime. And so they start down at latitudes around 20 to 30 degrees, or even a little bit further south than that. And then they migrate because of all the wind patterns and the rotation of the Earth. Well, they don't stop until they hit land. If it stays out in the ocean, all that warm water and all that heat there will just keep spinning out there forever. That's kind of what happens with Jupiter. Jupiter's red spot, this high pressure region here that's spinning around, well, it's stuck between these two cloud bands, so it can't move north or south, and so it just keeps spinning there. And so we think it'll probably go away eventually, but then another storm may come back in. But that's why it's been there for 500 years. There's no land or anything to slow it down. It doesn't migrate north or south with